Hello everyone, this is Math with Zanger. Welcome to our officially first video of AP Calculus BC. Unit 1, Limits and Continuity. And this video will cover 1.1, Limits. I will cover some definitions, some examples, limits in graphs, and how to determine the limits. 1.11, Limits. Before we formally define limits, let's start with the basic idea. A limit describes what value a function is getting close to as x gets close to a certain number. In this example, x is approaching 1. From the left side, the value of fx gets closer and closer to 3. From the right side, the value also gets closer and closer to 3. So, even though the value at x equal to 1 is unknown here, the function is still approaching 3 from both sides. This is why we write the limit of fx as x approaches 1 is 3. Now we can write the general idea of a limit. If fx gets closer and closer to one number L as x approaches a number C, then we say the limit is L. We can write it like this. The limit of fx as x approaches C is L. The important idea is that x can approach C from both sides, and the function values should approach the same number. We're looking at the function fx equal to absolute x over x, as x approaches 0. When x is positive, the function equal to 1. That means from the right side, the function approaches 1. But when x is negative, the function is negative 1. That means from the left side, the function approaches negative 1. Because the left side approaches negative 1 and the right side approaches 1, they do not match. So the two-sided limit does not exist. A one-sided limit looks at the function from only one direction. A left-hand limit means x approaches C from values smaller than C. We write this as the limit of fx as x approaches C minus is L. A right-hand limit means x approaches C from values greater than C. We write this as the limit of fx as x approaches C plus is L. So one-sided limits help us compare that happens from the left and from the right. Now we can state the main rule for two-sided limits. For a limit to exist as x approaches C, the function must be defined on both sides of C, and the function values must approach the same number from both directions. In other words, the left-hand limit and the right-hand limit must be equal. But if the two sides are different, like in previous example, then the limit does not exist. 1.1.2 Limits in graphs. Now that we know a limit depends on what happens from both sides, let's practice reading a limit from a graph. When we look at this graph, the open circles show points where the function is not actually defined, and the filled dots show the real function values. But for limits, we care about where the graph is approaching, not always the filled dot. For example, near x equal to 2, the graph approaches y equal to 1 from the left, and it also approaches y equal to 1 from the right. So the limit is 1 even though the filled dot is at y equal to 2. So the function value and the limit can be different. Now we're looking at the limits at infinity. This means x is not approaching a specific number. Instead, x is going toward positive infinity or negative infinity. For example, with y equal to 1 over x, as x gets larger and larger, the graph gets closer to 0. And as x gets toward negative infinity, the graph also gets closer to 0. So this tells us the end behavior of the function. In this case, the graph approaches the horizontal line y equal to 0. Instead of x going to infinity, we will look at what happened when the function value itself goes to infinity. An infinite limit happens when x approaches a specific number, but the function values grow without bound. For example, in the graph y equal to 1 over x minus 1, as x gets close to 1, the graph shoots upward or downward near the vertical asymptote. So we may write the function approaches positive infinity or negative infinity. But the infinity is not a real number, so this is describing the behavior of the function. It means the ordinary limit does not exist as a finite number. Now we're moving into 1.1.3 Determine limits. We will use limit laws, composite functions, and the squeeze theorem to find limits more efficiently. Let's start with the basic limit laws. These are the main limit laws. The idea is that if two limits exist, then we can combine them using normal algebra operations. For example, the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. We can also multiply limits, divide limits, move constant outside, use powers, and use roots. The only important warning for division, the denominator limit cannot be 0. So limit laws help us simplify complicated limits step by step. After basic algebra rules, we can also apply limits to composite functions. A composite function means one function inside another function, like f gx. The main idea is simple. First, find the inside function gx is approaching. If gx approaches L, then we can plug L into the outside function f, as long as the limit works. So instead of evaluating the whole expression at once, we handle the inside part first, then apply the outside function. Finally, there's one more useful theorem for limits that are hard to find directly. This is the squeeze theorem, also called the sandwich theorem. The idea is that if one function is trapped between two other functions, and both outside functions approach the same value, then the middle function must approach the same value too. So, if gx is below fx and hx is above fx, and both gx and hx approach L, then fx also approaches L. This is useful when the function looks complicated, but we can squeeze it between two simpler functions. And that's the first video of AP Calculus BC. Please follow for the rest.